Hello friends, in this video I'd like to solve the following problem from the United States of America Mathematical Olympiad 2023, problem number 2. We wish to find all functions from the set of positive numbers into itself, we are dealing only with positive numbers, such that the following functional equation is satisfied. F of x times y plus f of x equals x times f of y plus 2 for all positive numbers x and y. This problem is rather lengthy and rather hard, I'd say, and I will give you a bunch of hints, but you shall see that this problem needs some knowledge of linear algebra, in particular of solving linear recurrences. So first hint, establish that our function is injective, but this time it's not that easy to show injectivity by some well-known properties. You have to do it by hand. That is, take two arguments x0, y0, which are positive numbers, and suppose that f of x0 equals f of y0, and show that x of 0 equals y0. That would mean that our function is injective. Then, instead of x, put f of x, and the right-hand side of our equation will become symmetric with respect to x and y. You should be able to use the symmetry and injectivity to find f of x in terms of x, f of x, and some constants, f of 1 and f of 1. And then you should consider the following sequence, where an denotes the nth composition of our function with itself, and find recursion for this sequence. This recursion will be linear, but not homogeneous. And here comes the complicated part. You need to be able to solve this linear, not homogeneous recurrence. The fastest way is by characteristic polynomial. If you don't know what I'm talking about, either look it up on Wikipedia or Google or something. If you type into Google something like solving linear recursions by characteristic polynomial, you will get the overview of this method. Or stick with me and I will also cover it briefly. And then watch out for the multiplicity of roots of this characteristic polynomial. And then, the funny part, remember that we are only dealing with positive numbers, which should be able to tell us something about coefficients of our solutions. I know it's rather vague, but you will see in a moment. This problem is really beautiful. So give this problem a try if you want, and I will see you in a minute. Okay, so first of all, as I suggested, let's establish injectivity. So let's suppose that f of x of 0 equals f of y sub 0 for some x0 and y0, which are positive numbers. What do we have? Then, let's take a look. Let's take our right-hand side. On the right-hand side, we will have x0, f of y0 plus 2, and we know by our recursion, not by recursion, but by our functional equation, that it's the same as f of x0, y0 plus f of x0. And now notice the following. Here I can change the order, y0, x0, and f of x0 is by assumption just f of y0. And now I can use my functional equation again but with x and y flipped. So x0 stands in place of y0 and vice versa. So we have the following: y0 f of x0 plus 2. Okay, very nice. Which means that x0 f of y0 equals y0 f of x0, because here we have plus 2 and here we also have plus 2. And remember, again, f of x0 is f of y0, so I can write, instead of y0 f of x0, y0 f of y0. And now take notice that I can safely divide by f of y0, because our function, its range, it's just only positive values are attained. So I do not divide by 0. So that means that x0 equals y0, which exactly proves that our function is injective. Let's write it in pink. So we know that f must be injective. Very well, so now we know something. It will be helpful. And now let's take again our functional equation, but instead of x, let's change x to f of x. Then let's notice that we get the following. On the left hand side, we have f of x times y plus f of f of x. Okay, so we have f of x times y plus f of x equals f of x times f of y plus 2. But if you look closely, the right hand side is symmetric, so I can change x to y and y to x, and I can write f of y times x plus f of y. Okay. Okay. And also let's do the following. I will mark the first function in pink, and let's take a look. F of something equals f of something else. Our function is injective, so by injectivity, we have the following: f of x times y plus f of x equals f of y times x plus f of y. Okay, now we know something. And you know what? Let's set first of all, let's set y to be 0, and moreover, I don't want to write too many symbols, so I will also set r, which is by definition will be f of 1, and s will be by definition f of 1. And I have now the following: f of x plus f of x. Let's put this term also on the left hand side. F of 1 is by my convention just r, so I have minus rx equals, and here I have f of 1, which is by my convention just s, where r and s are some positive numbers. Okay. So now let's mark it asterisk. It's very important. And let's see. Notice that if I change my x, changing x to f compose with f composed bunch of times, let's say n minus 2 times of x, we get the following. Here on the left hand side I will have f composed with f and so on, n times in total. Here I will have f composed with itself, but only n minus 1 times. Here I will have r times f composed with f and so on, n minus 2 times equals s. And that suggests that some type of recursion is going on. And also, for the sake of brevity, I will let an of x to be, by definition, f composed with itself n times of x. It's a function of x, but also of n for natural numbers from 0. Okay, by convention, if n equals 0, I just define it to be identity. So a0 of x will be just x. And notice that we have the following recursion going on. Namely, a0 of x, it's x. a1 of x is f of x. And an of x plus an minus 1 of x minus r times an minus 2 of x equals s. And that holds for n which are 2, 3, 4, and so on. Okay. And now, this is a linear recursion because these numbers which stand here, here, and here, and here, they are just some numbers. They do not depend on x, they do not depend on n. So let's write it. A n of x is given by linear but not homogeneous recursion. What do I mean by not homogeneous? Well, s may not be 0. It can't be 0, in fact, because it's f of 1. And now, here comes the tricky part. There is a well-known method of solving these types of relations, these types of recursions, namely by defining so-called characteristic polynomial. If you are not familiar, it goes like this. We take our recursion, only the linear part, so only the left-hand side, and let's call our characteristic polynomial, I don't know, Greek letter chi may be useful because it stands for characteristic. And characteristic polynomial or subvariable, let's say of t, we just put, we go from the right, we have minus r, then we take this number right here is 1, and we multiply by powers of t. So we have t times 1, and here we have 1 times t squared. So this is our characteristic polynomial of our recursion. Okay, and now we factorize it. We need to factorize it. So it's characteristic polynomial. of, let's call this recursion, I don't know, square, relation square. And let's factorize it. Well, the factorization is, we can do it by quadratic discriminant. So quadratic discriminant, capital delta, it's just 1 plus 4 times r. So we have two roots. One root, so roots of chi, let's say. One root, I will call it alpha. It's minus 1 plus 4r over 2. And the second, it's square root of 1 plus 4 times r minus 1 over 2. Okay. And let's investigate these roots. The first root, it should be pretty clear that the first root is a negative number which is less than 1. Again, why is that? Well, because r is positive. So we have here 1 plus something greater than 1, so our numerator is greater than 2, over 2, so this entire fraction is greater than 1, and here we have minus in front. So it's justified. While the second root, let's take a look. Well, this number is greater than 1, so this number is necessarily positive. And moreover, one more thing will be very important. Moreover, the absolute value of alpha is greater than the absolute value of beta. It should be visible because if you take absolute value in case of alpha, you just remove the minus sign, and here we have 1 plus square root, and below we have square root minus 1. The number above is pretty obviously greater than the number below. Okay. And now that means, or one more thing. That means that we have two cases now. We have two cases. Since, so you know what, maybe to be clearer, I will take again my recursion, an plus 2 of x plus an plus 1 of x minus r times an plus 1 of x equals s, and I will artificially write times 1 to the power of n. And the general method for solving non-homogeneous linear recursions is to take a look at the right-hand side. On the right-hand side, we have s times, crucially, this number, 1 to the power of n. Let's treat it as our third root, gamma. And we have two cases. Well, alpha cannot be equal gamma, but beta can be equal gamma, in special case where r equals 2. And now we have two separate cases, subcases, one can say. Case number 1 will be if beta doesn't equal gamma. And here will be case number 2 if beta does equal gamma, which is 1. And I will cover these both cases separately. In the first case, the general theorem about solving these types of recursions says that an of x equals a of x times alpha to the power of n plus b of x times beta to the power of n plus c of x times 1 to the power of n, but 1 to the power of n is just 1. While in the second case, since one of our roots have multiplicity of 2, the general form of solution is a of x alpha to the power of n plus n times b of x plus c of x, where a of x depends on x but doesn't depend on n, while alpha doesn't depend neither on n nor on x. Excellent. Question: how can we find a, b, and c? Well, they can be found from our recursion. So, from our initial conditions, I should say. Because we have 3 variables in each case. You know what? Maybe I will cover first only this case. Second case will be left for later. How can I find a, b, and c? Well, when x equals 0, when n equals 0, we have the following: ax plus bx plus cx, and remember that a0 of x was defined to be just x. If n equals 1, I have the following: alpha a of x plus beta b of x plus c of x equals f of x, because a1 was defined to be just f of x. So now I have 2 equations, but I have 3 variables, a, b, and c. How can I find the third equation? Well, the third equation can be obtained by plugging this general form of solution in our recursion. What do I mean by that? Remember that an of x plus an minus 1 of x minus r times an minus 2 of x equals s. Okay, and now if I plug in, let's see what happens. If I plug in the numbers, I will have a of x times alpha to the power of n plus b of x times beta to the power of n plus c of x plus a of x alpha to the power n minus 1 plus b of x beta to the power n minus 1 plus c of x, and finally minus r times a of x alpha to the power n minus 2 minus r times b of x beta to the power n minus 2 minus r times c of x, and that should be equal s. And now let's take a look. These 3 numbers in our first column, their sum is just 0. Why is that? Because remember that alpha squared plus alpha minus r times alpha is 0. Why is it 0? Well, because it's defined exactly to be the root of this polynomial. By the same argument, this part right here is also 0, because beta is also one of the roots of this polynomial. And we have, finally, 2 times c of x, or maybe write it as 2 minus r times c of x equals s. And if you look closely, maybe I will bring these 3 conditions together. A plus b plus c equals x. Alpha a plus beta b plus c equals f of x. And finally, 2 minus r c of x equals s. And from these equations, you can get a, b, and c. And now, here comes the most important observation of the entire reasoning. Let's take a look at, so let's fix x. Treat x as a fixed number. alpha is negative. And also, you know what, I will write it as in the following way, because I need a fourth crucial equation. I will take a n of x in the following form. I will take alpha to the power of n in front, and I will have a of x plus b of x. Here I will have beta over alpha to the power of n plus 1 over alpha to the power of n times c of x. And now, think about it. What happens when n gets bigger and bigger, but it's odd number? What happens? Well, if n gets bigger and bigger, remember that beta over alpha has absolute value which is less than 1. So this part goes to 0. This part also goes to 0 because absolute value of alpha is greater than 1. And this is a constant with respect to n. We are talking about with respect to n. And now here comes the crucial part. If x is fixed, this number is either positive or negative. And this part changes sign with alternating between even and odd numbers. So this is alternates between positive and negative values. And if this were to be non-zero, if a of x were to be non-zero, if a of x is non-zero, then it's obviously, then it is either positive or negative. And it's a problem. Why? Because remember that every term of our sequence is positive. Every term of our sequence is positive because we are composing functions whose range is a subset of positive numbers. So it cannot happen. It cannot happen because for sufficiently large n's, we will get a negative value. Certainly we will get a negative value if a of x is non-zero. If a of x is 0, this problem will not happen. And in fact, it's the only option. A of x must be 0. In other cases, we will get negative values in our sequence for sufficiently large n's. Crucial observation. So I will write it. If a of x is non-zero, we will get a n of x which is negative for sufficiently large integers, even or odd, doesn't matter. We just need one to break our condition that our sequence is non-negative, is positive in fact. And that means, which is impossible. This is impossible. This is in fact impossible, which means only one thing, crucial. A of x equals 0. Okay. And you know what? I will take my system of equations and I will write it once again with our final fourth equation. I'm running out of space, which is a problem, which can be easily solved. Okay, so what to do that? Okay. Going back. I have my system of equations with our fourth crucial equation. A of x equals 0. Okay. And now let's solve this system of equations. Well, if f of x is 0, from the third equation, it doesn't really matter, but we see that c of x is constant. Because s is constant and r is constant, doesn't depend on x. So, and from the first equation, we see that a is 0, c is a constant, so b of x equals x minus c. And let's take our second equation, or maybe, you know what, I will write it in Roman 2. And I'll have the following. This is 0. We have beta times b of x is x minus c plus a constant is f of x. And that means that our function must be affine, because it's some constant times x minus some constant plus c. F is an affine function. Okay, so now we know that our function must be affine. In this case, because remember, it's the first case, we have also the second case where beta equals gamma. So we have to consider now the second case. What happens now? Well, so remember that alpha, the first root is some number between minus infinity and minus 1. Yes, because of what? Because of this. We have established it. Okay. And now also we need equations for a, b, and c. First equation, again, will be obtained when we set n to be 0. When n equals 0, I have the following. A of x plus 0 plus c of x equals x, because it's our 0th term. If I plug in n to be 1, if I set n to be equal 1, I have ax times alpha plus bx plus c. It's f of x. Two equations. How do I get the third equation? Again, by using the recursion. Remember, once again, you know what, I will copy it. Now we use our recursion. And we get the third equation. Okay, so let's put it. So we have a of x alpha to the power of n plus n times b of x plus c of x alpha minus 1. So we have plus a of x alpha to the power n minus 1 plus n minus 1 b of x plus c of x minus r times a of x alpha to the power n minus 2 minus r times n minus 2 times b of x minus r times c of x, and all of that equals s. Again, we play our game. This part is 0. It's 0 because alpha is the square root, square root of our characteristic polynomial. And what do we get? We have, let's take a look. We have n times b of x plus n minus 1 times b of x minus this many times b of x. So we have 2n minus 1 minus rn plus 2 times b of x. And we have 2 minus r times c of x equals s. But remember one more thing, that if we are in second case where beta and gamma are equal to 1, and let's go back, that means beta is 1 in this case, and beta can be 1 only in one case where r equals 2, because when r equals 2 we have square root of 9, which is 3, 3 minus 1 is 2, 2 over 2 is 2. So that means that r equals 2. So we have a simpler equation. 2n minus 2n is gone, minus 1 plus 2, plus 2 times r was missing, minus r times minus 2 is plus 2r. So we have 3b of x equals, this vanishes, and it's equals s. So it's our third equation. And also, let's play our game once again. Remember, so let's take our recursion once again. An of x, I will put alpha to the power of n in front. I will write it also in blue. Alpha to the power of n. In parentheses, I have a of x plus n times b of x plus c of x over alpha to the power of n. And again, let's ask ourselves, can a of x be non-zero? No, because of the very similar reasoning. Here we have a polynomial, and here we have an exponential function with base of absolute value greater than 1. So this part right here goes to 0 as n goes to infinity. And this part again alternates between positive and negative values. If this part were to be non-zero, we will have at some point a negative value in our sequence, which is impossible. So by reasoning similar to that done before, we have a of x equals 0, must be equal to 0. Okay. And let's take our 4 equations. Which 4? These 2 equations. These 2 equations. The third equation was this one. And the fourth one, again, a of x is 0. And let's deduce something about our function. Well, from the third equation, again, s is a constant, so we see that b of x is a constant, doesn't depend on x. And we see from our first equation that c of x is just x, because a of x is 0. So by plugging it into equation number 2, 2 becomes the following: 0 plus b of x, but b of x is some constant, so let's call it b, plus c of x, but c of x is x, equals f of x. Again, f is an affine function. F must be affine. In both cases, we have reached the very same conclusion, that our function must be affine. Because here, f must be affine. If you go back, same conclusion was reached before. And now we are almost at the end of our proof. It's now time for verification step. Verification. verification. So since f is an affine function, f of x equals, you know what, let's write it p times x plus q for some constants p and q. And now let's take this function and plug it into our first initial functional equation, which was right here. F of x times y plus f of x equals f times f of y plus 2. Do I remember this equation? Yes, I do. Okay. So let's write it. So our equation is f of x times y plus f of x equals x times f of y plus 2. Okay, and let's plug our numbers. So we have here f of x times y plus p of x plus q. Here we have x times p of y plus q plus 2. And again, here we have p times this quantity plus q. And here we have x pxy qx plus 2. And let's multiply pxy plus p squared x plus pq plus q equals pxy plus qx plus 2. And remember that that should be true for every real number x and y, for that matter. Well, this is exactly the same as that. This is exactly the same as that. Yes. And what else? Well, here we have p squared x, and here we have qx. That means only one thing, that p squared must be equal to q. What else? And here we have a constant, and here we have other constant. So pq plus q must be equal to. And I'm running out of space once again. As you can see, this problem is lengthy. Okay, and now we need to solve these two equations. Well, from the first equation, we can plug in into our second equation, and we get p to the third power plus p to the second power minus 2 equals 0. And now, finally, we have to do a factorization of polynomial. Let's guess a root. One obvious root is 1. So we can do the following factorization: p cubed minus p squared plus p squared minus p plus 2p squared minus 2 times p plus 2 times p minus 2 equals 0. P squared, p minus 1, 2 times p minus 1 plus 2, p minus 1 equals 0. P squared plus 2 times p plus 2 p minus 1 equals 0. And let's take a look. In our first parentheses, it can be written as p plus 1 squared plus 1, p minus 1 equals 0. What are the solutions? Well, this parenthesis cannot be 0, so p must be equal 1. P equals 1. And what about q? Well, q was p squared, so q must be equal to 1 as well. So our only solution, our functional equation has only one solution. The only solution of our functional equation is f going from the set of positive numbers into itself, given by the formula f of x equals x plus 1. Well, one last remark. Is its range in the positive numbers? Yes, it is, because if we add a positive number and 1, we also get a positive number. So in fact, this is our solution, and this is the only solution. And that closes our problem. So as you have seen, what to get from this problem? Well, I wish that you remember, first of all, checking injectivity, using injectivity, and then if you get some type of recursion, when you can compute the next composition of function in terms of previous compositions and other constants, it's sometimes a good idea to consider a sequence of these compositions, as I have done here. Yes, I have considered an to be the nth composition of my function, to find a recursion and to solve it. Again, the easiest way of solving linear recursions is by characteristic polynomial. Is by finding characteristic polynomial, by finding its roots, by finding the multiplicity of roots. And if you happen to get a non-homogeneous or inhomogeneous recursion, then write the inhomogeneous part in terms of power function, exponential function. In this case, it was just 1 to the power of n. It's our third root. And either if we have 3 distinct roots, then the general case is some constant times first root to the power of n plus another constant times second root to the power of n plus third constant. In our case, it was not exactly constant, it was dependent on x, but not on n. On the other hand, if you have a root of multiplicity 2, for example, instead of having second root to the power of n plus third root and so on, you get a polynomial of degree 1. So you have n times some constant plus constant. It can be taken further. For example, if you have a root of multiplicity of 3, then you would have a quadratic polynomial, and so on. Again, please educate yourself, read something about this method on Wikipedia or on the internet, or consult your local, I don't know, discrete mathematics textbook, linear algebra textbook, something like that. This method is extremely useful, and it's paramount that you be familiar with this method if you are preparing for some hard type of functional equation, because it's not the only problem where this type of reasoning appeared. Maybe I will provide in the description a suggestion for another problem where very similar reasoning leads to our goal. Okay, and I will leave you at that. So I hope that you've learned something new. I hope that you were entertained. Thank you for watching. I wish you a nice day, and I will see you next time. Goodbye.